Okay, so thank you very much for the introduction. So I'm going to now present interdisciplinary work at the intersection of computer science and finance. This is joint work together with my advisor Sven Zeuken and with Stefano Battiston. And so as my motivation, I chose not the Lehman thingy, but another financial crisis, which is the East Asia financial crisis in 1997. And so we visualize this crisis as follows. You have the banks or financial institutions in Indonesia, South Korea, and Thailand, represented by the points. And the arrows represent liabilities. So for example, this bank would owe an amount of 2 to this bank. And now in this financial crisis, about 50% of all the banks were bankrupt. But the problem was, it's not so easy to decide which banks actually are bankrupt and which are not. Because, for example, if this bank can pay this amount of 2, depends on whether it receives money from this bank, and this depends on whether it receives money from this bank, and so on. As a Nobel Prize-winning economist and then chief economist of the World Bank, Joseph Stiglitz, puts it, you couldn't tell whether they were bankrupt or not, because that depended on whether they got paid money that was owed to them by other firms, might or might not be in default, depending on whether the firms that owed them money went bankrupt or not. So the World Bank had the same problem I just described, and that caused a lot of trouble to them, at least Stiglitz says. And so formally what Stiglitz wanted to solve and couldn't is what we call the clearing problem. We are given a set of banks. The banks have some assets that are external to the financial system, for example, stock. We're just going to model this as cash in the following. And there's a set of contracts between the banks that define what the banks should pay to each other. We are then looking for the collection of what we call clearing payments that describe what the banks actually can pay or will pay to each other, subject to the standard bankruptcy regulations. For example, if I'm bankrupt, I have to pay out all I have to my creditors. I cannot keep anything for myself. These kind of regulations. Now, just to make sure we're all on the same page, this is a static model. The contracts do, in our model, they don't have a built-in timing, and therefore also the payments happen all at the same time. So these are simultaneous. Let's take a step back again. Why do you want to solve this problem? I've shown you an application in resolving financial crises. Another natural application where you need it are network stress tests, where a regulator, such as the European Central Bank, would essentially simulate the financial crisis to test the stability of the financial system. If you want to take all the network effects into account, you need to solve something like the clearing problem. In the third step, we may want to take the expectation over all possible economic scenarios in such a stress test and perform network valuation on a bank. Now, let's look at what has been done on this problem so far. Yeah.
Is it clear that the answer is always yes or no? Couldn't there be scenarios where both situations are possible? That some banks are...
sorry, yes or no regarding... what's the question to yes or no?
Given...
Is the set of clearing payments unique, or might there be more than
yeah.
Oh,
one?
yeah. I think this is an excellent question, and I'm going to get back to this in a moment, okay? Right, so there are two modeling decisions you need to make, also to answer your question. The first is, which types of contracts do you allow? And the second is, do you have default costs or not? This means, is money lost in the process of bankruptcy, or is it all preserved and paid out to the creditors? And in prior work, it was shown that if you have only debt contracts, and that answers part of your question, then clearing payments always exist. They are also almost unique. You have a canonical solution in this case, and they are also tractable to find. So we have a polynomial time algorithm for the problem. Yeah, so this was shown after 97. Okay, so it didn't help Stiglitz at that point. The goal of our work is to extend the set of possible contracts to CDSs, or credit default swaps. These are derivatives that are motivated as follows. Let's say we have a bank, B, and it is owed money from some bank A. But B might worry about that A might not be able to pay this. So B might worry about the default of A. And now B can buy an insurance on the default of A from a third bank, C. And this is a contract that creates a liability from C to B as follows. C owes an amount of this notional 2, and then multiplied by 1 minus the percentage of liabilities that A can pay. This is also called the recovery rate of A. Now if you do the math, and if you assume that C cannot fail, which might or might not be realistic, then B is completely insured against the default of A. If you don't assume that C cannot fail, then his insurance is not complete. And in the real world, this contract might not be present, but this might still be. And now our financial networks look like this. We have both these debt contracts, like this one, and we have CDSs like this one. And now we are asking again the question, do we have existence and tractability? And we have shown in prior work that if you have both default costs and CDSs, then you might not have existence. So clearing payments might just not be defined. And it's even NP-hard to decide if they are defined in a certain instance. So this was our work from last year. Now what I want to talk about today is this last free square here. What happens if you don't have default costs, but you still have debt in CDSs? And I will show to you that in this case, clearing payments always exist, but they are PPAD complete to find. And so this situation is similar to the problem of finding Nash equilibria, where we also know that the Nash equilibrium always exists. It's not unique. The set of Nash equilibria does not necessarily have a nice structure. This is also true here. And it's also PPAD complete to find. And actually we will use techniques from this problem to prove this. So let's think for a moment about the implications of these results. I see two main implications. The first, rather practical one, is for network stress testing. Intractability of the clearing point in this case implies that networks with CDSs cannot efficiently be stress tested. And of course that's a huge problem for the regulator, because if they want to take all the effects into account, they cannot see which banks are the risky ones and which are the stable ones. And in a more positive way, our results contribute to a literature where people are trying to understand what makes financial networks complex in a more general sense. And we can contribute to this a very precise statement. Adding CDSs is like going from P to PPAD. Good, so I would now like to make everything formal and everything precise. So I'd like to first show you a formal model. We have a set of banks. We model single banks like this. This is going to be a picture. Each bank has some external assets which are understood as cash and which are just modeled as real numbers. For any two banks I and J, we store the total debt from I to J. And for any three banks I, J, and K, we store the notional of the CDS from I to J on K. If these contracts don't exist, we put 0. And then we assume some further sanity conditions, so we don't accept all the combinations of these numbers, but we have some conditions that make these networks realistic. I don't want to go too much into detail. Right, now what we are looking for are recovery rates. Remember, the recovery rate of some bank I is the percentage of liabilities bank I is able to pay. And so if we are given a candidate vector of recovery rates, we can compute a few things. We can first compute the liabilities from any bank I to any bank J by just making the debt. And then we are summing over all possible reference entities, the one with the dashed line, the CDSs, and then we take the notional of the CDS times 1 minus 3 and 3. So the important thing is that the liabilities actually depend on the recovery rates here. Of course, we can also compute the total liabilities of bank. We can compute the payments from any bank I to any bank J by just multiplying liabilities with the recovery rate. This is the definition of the recovery rate. We can compute the total assets of a bank. This is what a bank has by taking the external assets plus all the incoming payments of the bank. And now finally we can define what it means for a vector of recovery rates to be clearing or a solution to the clearing problem. As follows, so we call it clearing if the recovery rate is the assets divided by the liabilities, and then we restrict this to the interval 0, 1, because the recovery rate cannot be above 100%. And if this is 0, then we just make no restrictions, because if you have no liabilities, then your recovery rate doesn't matter. So we just say everything is okay. Good. So we can prove that such a solution always exists. The proof is by continuity of this function ai divided by li, and then you apply a fixed point theorem. But it can also be that you have only irrational solutions. And this is also new with CDS. This doesn't happen with that. And so we introduce an epsilon error into this formula. We put it here into the bracket. If you want to know why into the bracket, ask me up to the top. And now the search problem we're interested in is what we call epsilon fine clearing. Given a financial system, find an epsilon solution. And we can prove that this is actually a well-posed problem. So this thing here actually always exists, of course, and also is not too long. So it's polynomially long and is in PPAD. This is by finding a Lipschitz constant on this quotient. Yeah.
Is this definition of the liability of A divided by L is what is done in practice in
yeah, so some people sorry. So in the literature this is sometimes just used as the definition of the recovery rate. But this definition is also motivated by these standard rules of bankruptcy law. I don't think I have the time to go over it now, but these are like 3 rules, and we can maybe do it. Yeah. Right, so this is our search problem. Let's get to the interesting part of the talk. Let's show that it's PPAD-hard. And so in detail we show that epsilon fine clearing is PPAD-hard for a sufficiently small constant epsilon. So this is the strongest of these types of statements. We could also think about polynomially small epsilon or even exponential, but we show it for constant. And in effect, there's no polynomial time approximation scheme with epsilon solutions, unless P is PPAD. And so from a practical point of view, this would mean there is no good stress testing algorithm that is guaranteed to be fast for these networks. Now, we do this by reduction from the generalized circuits problem. For those of you who don't know them, a generalized circuit consists of approximate gates. So we have arithmetic gates, we have an approximate comparison gate, and we have approximate Boolean gates. And they are connected in an arbitrary way. So they may also have cycles. And this turns the problem of actually evaluating a generalized circuit into a fixed point problem. And Rubinstein showed in 2015 that this fixed point problem is actually PPAD-hard. So the problem is, it's called epsilon G circuit. Given a generalized circuit, find an epsilon solution. And so now the natural approach for our proof is reduce epsilon G circuit to, well, epsilon third fine clearing. So we reduce the epsilon here a little bit, which doesn't matter because it's a statement about the existence of some epsilon. And all we need to do to achieve this is to express the gates of the circuit as certain financial systems. This is what we call financial system gadgets. And everything else is automatically done in the proof, so we don't need to worry about error accumulation or anything like that. So these gadgets are going to have error plus minus 3 epsilon, not epsilon, and this is why we divided by 3 above here, and these cancel out. So I'd like to show you one of these gadgets and discuss the principles how we create them. So this is the addition financial system gadget. And the way our construction works is that the information, the signal in the circuit, travels along the recovery rates of the banks. So we have two input banks, A and B here, that belong to some financial system we have already constructed. And we have an output bank V here, and we construct this such that the recovery rate of V is equal to the recovery rate of A plus the recovery rate of B, restrict to 0, 1, plus minus 3 epsilon. And these are always built in such a way that there is some source bank that is very highly capitalized, so this can never default. It's a source of value, or like a power source in an electric circuit. And a sink bank. The liabilities of all the banks are 1, so these are trivial. And the banks that do the actual computation, these ones, are connected to each other using CDS references. So the flow of information is always using these CDS references. Banks never owe money to each other. And now if you do the math, and you can just trust me for the moment that if you can compute the recovery rate of this, and then of this bank, you actually receive this formula. And the error is 3 epsilon because you have 3 banks, and you have 1 epsilon at each bank. Now this could be referenced in another CDS, which would be used in another gadget, and so on. And in the end, you have built your whole circuit. And this is how we do it. To conclude, today I have talked about the problem of finding clearing payments in financial networks with credit default swaps and without default costs. I have shown that the epsilon fine clearing problem is PPAD-hard for sufficiently small constant epsilon, which implies that there is no PTAS. And I have done this by showing you financial system gadgets that provide a reduction from generalized circuits. In future work, it would be really nice to know how small actually this sufficiently small is. It would be something you could tell the regulator. If this is 5%, they might be very worried. If it's like 10 to the minus 100, maybe not so much. Of course, this result is not affected by this being small, but still would be something nice to know. And then it would be nice to have an algorithm that is fast in practice, even though not polynomial. This could work by iterating over different sets of defaulting banks. In our working paper, we actually have proven that it is already PPAD-hard to get this right. So which banks default and which don't. And so we believe that this would be a nice point to capture the complexity of the problem. Thank you very much.
Can I ask the next speaker to come set up while we take questions?
Questions?
We also looked at, in some sense, the question of how much external money would need to be injected so that you can actually, all the liabilities can be satisfied and things will clear, kind of.
Yeah, so I think if you want to save all the banks, then this is like close to the total liabilities in the system or something. So I think this amount could be huge. I believe. So I think another interesting problem in this line would be how much money do you need to inject in the case with default costs, where a solution might not exist, to guarantee existence of a solution. And this is something I haven't thought about it in too much detail, but I think it's an interesting point.
Thanks, Stefan, again. Abhinav, presenting testing submodularity.